Hi-oh, here we are one more time. This time we're going to finish up the unit talking about something called transformers. You've seen them before, and I'm not talking about robots in disguise. Our little device up here on top of the telephone pole. This is a very basic transformer. You've seen the big ones fenced in that help change the voltage as it's coming from the power plant to a neighborhood. These things are called transformers. You've seen them when you've plugged your computer in or some other device to charge it. The big blocky thing on the end is called a transformer. Transformers work on the idea of electromagnetic induction. What do I mean? Well, we know a coil or a wire that carries a current produces itself a magnetic field. And we know a magnetic field will produce a current. So, if we were to oscillate that original current, in other words, alternating current, the magnetic field will oscillate too. And if this changing field is brought near another coil, it'll induce a current in the other field. So one produces the other, and they don't even need to touch. A transformer is nothing more than a device that specifically changes the voltage. A byproduct is that the current will also change. There's some general knowledge terms that you need to know. The input side, in other words, the side you plug into the wall, you hook it up to a battery, that's called our primary. The output side, the one that your computer hooks up to, the one that goes to some game, that's called the secondary. And of course, the number of loops we call the turns of the coil. Mathematically, we'll just use an N to represent that. We have two different types of transformers. We can either step up, and remember, transformers are specifically designed to change the voltage, so we can step up the voltage, or we can step down the voltage, in other words, decrease it. And this is based on the number of coils. A real simple trick to whatever you're going to see. You're going to see a lot of math coming up. But the real simple trick is count the coils. If there's twice as many coils on the input side compared to the output side, try that again. If there's twice as many coils on the input side compared to the output side, we have less coils, therefore less voltage. So it's a step down. If it's the opposite, then it's a step up. So whichever side has the most coils is the one that has the most voltage. If it has 4 times the coils, it has 4 times the voltage. So let's do a little review and talk about the components of a transformer as well. The components for a transformer, if you haven't realized, is just a coil of wire and something to produce a current. It's nice if you have a bar or something to connect the two, but it's not necessary. For a motor, it's a wire, a magnet, and you have to move one of those with respect to the other. And same thing with the generator, they're both the same. With a motor, the input side, of course, is electricity, and you get motion out. With a generator, you put motion in, and you get electricity out. The purpose of a motor is to, well, make motion. And the purpose of a generator is to make electricity. What about a transformer? Input is electricity, output is electricity. Actually, the input is a voltage, some voltage, and the output is a different voltage. So the purpose is to change the voltage. So here we have a nice picture. We have some information here. We have voltages. We have the number of turns around each side of the transformer. We have the current. We have the power. We have all sorts of stuff. The reason why I have power on here is because, check this out. We know from before, power is current times voltage. So look at this. The power on this side is 120. And we also know something. Tanstaffel. You can't get something for nothing. 120 watts in, we get 120 watts out. And look what we can do. We can use the same formula and we can find out what the current is. So 120 on this side. Look what happened to the voltage. The voltage doubled. So the current has to be cut in half. It turns out it's a half an amp. We also have a formula that relates the number of coils on each side, P is for primary, S is for secondary, versus the voltage. We can also rewrite this as a ratio of the voltage of the primary to the voltage of the secondary is equal to the number of coils in the primary versus the number of coils in the secondary. Both formulas work, and you can see it happening here. In fact, both cases, let's focus the one on the right. Look what happened to the number of coils. We have half the number of coils in the output, therefore we have half the voltage. On our original one, the one on the left, we have twice the number of coils and therefore twice the voltage. The one on the left is a step up. We've increased the voltage. The one on the right is a step down. We've decreased the voltage. So let's take a look at this. Think about what we know and what we have. The original voltage is 4. So that's our original is 4. We'll put 4 here. The original coils is 10. The new coils, that's what we're solving for. The new voltage is 12. And if you solve for this unknown, you'll get 30. There's 30 coils. Well, think about this. If we have 3 times the voltage increased 3 times, the coils should have as well. Or we mentioned you can't get something for nothing. Power is conserved. Power is voltage times current. And because you will change the voltage, you will inevitably change the current because that power can't change. Remember, these little P's stand for primary side and the little S's stand for secondary. What about this example? Right, the input power, let's find that, is current times voltage. That turns out to be 120. What do you know? It's the same. Remember, what you start with is what you end up with. The output side, current times voltage, is 45. So what must we have put in? 45 watts. Let's talk about the coil ratio. We can, remember, change this formula to make a ratio of the voltages to the ratio of the coils. Take a look at what we have, what our run-on, what our wall outlet supplies. Our wall outlet is our primary. So look, it's 120 to 12, and you can see that this is 10 times. All right, our input is 10 times greater than our output, and therefore the number of coils should be 10 times greater. So this is a 10 to 1 ratio. And likewise, we know our primary has to be 5 times greater than our secondary. So our secondary is 6 volts, therefore our primary should be 5 times greater, or in other words, 30 volts. Let's look at it a different way. Or we could just plug it in, or we can look at what's going on. The turns in the secondary doubled, therefore the voltage of the secondary should have doubled. Our primary is 15. If you plug in those numbers into our original formula, you'll find that to be 15. Look what happened to our voltage. It increased, so this is what's called a step up transformer. What about the other one? Our voltage decreased. Our voltage was cut in half, so our coils should have been cut in half as well, and this would be, of course, a step down type of transformer. Finally, let's talk about the path of this power, where we use some of these transformers. You see, it takes a lot of energy if we send the power with a lot of current. So if we can reduce the motion, the movement of those electrons, we reduce the current, we can limit our loss due to heat. So in order to reduce the current, we have to, of course, increase the voltage. And so our power plant produces a certain voltage. We use a transformer to step up the voltage, send it across country, and then come back towards your house where we drop it down to something that your house uses, somewhere between 110 and 120 volts. So that's the whole purpose for those transformers. So we can send stuff long distance without using a lot of electricity, losing it in the form of heat. The final thing to discuss is something you quite literally see every single day: light. Light is an example of induction. A magnetic field produces an electric field, and an electric field produces a magnetic field. And look at that, they're perpendicular to one another, those fields.